In this video, we are going to graph quadratic, cubic, square root, and cube root functions using a vertex or a point of symmetry and our knowledge about that function's transformations. In previous lessons, we've spent time looking at functions and determining what their transformations are. What I would like you to do is pause the video and answer, and I have 4 questions here. I would like you to answer either in your notebook or the inside front cover of your packet. So go ahead and pause the video now. Okay, you should have tried these on your own. The directions state, write the function rule in the form g of x equals for the following transformations of x. So our first function, I see it's already moved to the left 1. And now I'm transforming it an additional 1 unit left. So now it's left 2. It moves 3 units down. It has a vertical dilation of 2. Space here. So the leading coefficient needs to be a 2. For number 2, we see that the original function f of x has been moved up 1. And g of x is moving up 3. So now we are up 4. So I know it's going to be plus 4, but I also notice that I have a horizontal dilation. And whenever I have a horizontal dilation, I want to remember that that happens inside the parentheses, and it's going to be the reciprocal. Okay. So I'm going to have 2x in my parentheses squared, and then up 1 and an additional up 3 will be up 4. If you didn't see number 4, pause the video, do number 4. Okay, for number 3, we have a lot going on here in f of x. We see we have a horizontal dilation. It's moved to the right and down. Now we're going to reflect it over the x-axis and move it to the left. So I'm going to take my 3, that's the leading coefficient, the a value, and make it a -3. There's no right or left movement, so I'm going to leave the -5. Oh, wait, 9 left. I'm a big liar. So the 9 left, if I'm right 5 and I go 9 left, now I'm kind of left. So like if I'm 1, 2, 3, 4, 5, I'm here. And I go 1, 2, 3, 4, 5, 6, 7, 8, 9. Now I've gone from right 5 to left 4. And the -2. Okay, and then number 4, again, if you didn't have a chance to do number 4, if you couldn't see it, do it now. Pause the video. Now let's check. G of x, f of x has just moved down 3. So I'm going down an additional 5. So now it's going to be -8 total. 7 to the right. So in my parentheses, I know I'm going to need like x -7. Reflected over the x-axis with a vertical dilation of 1/3. So reflected over the x-axis, a vertical dilation of 1/3, right 7, already down 3, down an additional 5, gives us down 8. If you haven't checked your homework from last night on the answers posted, please go ahead, pause the video as needed, check your homework from last night now. Okay. In this video, we are going to graph in our packet, excuse me, 4 functions that are parent functions, and then use those transformations, use the transformations we learned about previously to come up with additional graphs. So first off, we have the parent function y equals x squared. So from algebra 1, maybe you remember that the vertex is going to be at 0, 0 on the origin. So I'm going to put 0, 0 in the center of my table. And then I'm going to go 1, 2, 3. And I'm going to square those numbers. 1 squared is 1, 2 squared, 3 squared. Then I'm going to go on the left. -3 squared, -3 times -3 is 9, 4, and 1. So I can easily graph this parent function 0, 0, 1, 1, 2, 4, 3, 9. And on the other side. And my quadratic function looks like this, and its shape is called a parabola. Now, the domain of this function, we want to remember that these are all of our x values the function covers. Now, I can square any number. I can square any x value, any positive number, any negative number, I can square it. And for this reason, we say the domain of this function is all real numbers. We abbreviate all real numbers with this R. It's kind of like the paragraph symbol, but it makes an R instead of just stopping at a P. And again, we say the domain is all real numbers because this graph stretches from left to right. Every single number can be squared. Now, when we look at the range of a function, those are our y values. And the range is what y values does this function produce? What kind of numbers come out of x squared? Well, I can see on my graph, I only have numbers that are greater than or equal to 0. I only have positive numbers. So my range is going to be y is greater than or equal to 0. For increasing and decreasing, it's important to make a note that these need to be x values. And I'm going to always read my graph from left to right. So I'm going to grab a highlighter and I'm going to start on the left side of my graph and I'm going to trace. And as I trace my graph from left to right, what's happening here in green? That's right, it's decreasing. So we see it's decreasing when x is smaller than 0. Here's 0. We're always using x values. Everything smaller than 0 is decreasing. Now, after 0, as I continue tracing from left to right, after 0, the graph is going up. After 0, the graph is increasing. So we're going to say this graph is increasing when x is greater than 0. Let's take a look at our next parent function. We call these parent functions because there's no transformations. So now we have the square root of x. Now, we've talked about this before. We can only input positive values. So we don't just want to be like 0, 1, 2, 3, 4. We're taking the square root. What numbers can I take the square root of easily? Well, the first number is 0. What number times itself is 0, 0? What's the next easy number? 1. What number multiplied to itself is 1? The next number I'm going to put in my table is a 4, because what number multiplied to itself gives us 4? I'm sure you can see the pattern here. I'm only going to use perfect square numbers. Now, if I wanted to, I could put in 16, 25. My graph doesn't go that far, so I don't even know that I can fit 9. 9 might be a stretch. So just make a little note in here. We only will input positive numbers in a square root. Like I'm not going to do -1, -4, -9. Also, I'm going to make a note to only select numbers that make the argument a perfect square. Remember, a perfect square is like 1, 4, 9, 16, 25. And I'm sure what you're wondering is, hey, Ms. Strauss, what is an argument? Let's just remember the argument is just a fancy word for the stuff under the square root. This is going to become important as we start to look at transformations. But let's finish graphing this parent function for square root of x, and we'll take a look at its properties. So we have 0, 0, 1, 1, 4, 2, and 9, 3. Oops, I missed. That's okay. So for the domain here is not all real numbers. I don't have any negative numbers, any negative x values that I can evaluate. I cannot take the square root of -4. There's no number times itself, no real number times itself that gives you -4. So here our domain is only going to be numbers that are greater than or equal to 0. Our range is only going to be y values that are greater than or equal to 0, because again, I also only have positive y values. I notice that this entire graph is increasing. If I grab my highlighter and I trace from left to right, this graph is only increasing. So I'm going to say it's increasing when x is greater than 0. I'm going to say it's never decreasing because it's never going down. Now, one thing I want to point out is that I'm not putting equal to signs in my increasing and decreasing intervals. And the reason is because as we increase and decrease at any turning point from increasing to decreasing or any endpoint on the graph, we're not really increasing or decreasing at that particular point. However, if you put an equal to sign under it on your increasing and decreasing intervals, I will not work it wrong. Our third parent function we are going to graph is x cubed. This function is also called a cubic function or a cube function. And I can cube any number I want. So I'm going to, again, pick nice numbers like -3, -2, -1, 0, 1, 2, 3. Now, if I cube -3, -3 times -3 is 9. 9 times -3 is -27. Here, I'm going to get -8, -1, 0, 1 times 1 times 1, 2 times 2 times 2, 3 times 3 times 3. So that's 0, 0, 1, 1, 2, 8. When I look at the domain of this cubic function, I don't see it. Oops, I didn't connect it. I don't see it going from left to right, covering all the x and y values. That's only because my graph isn't big enough. If I were to zoom out further, I can cube every single x value here. I can cube 10. I can cube -10. I can cube every number. And for this reason, the domain is all real numbers. Now, when I look at the range of this function, I have both negative values and I have positive values. I'm covering every single y value from bottom to top. So the range is all real numbers. Get my highlighter out. As I trace from left to right, I notice that this entire graph is increasing. Because the entire graph is increasing, we'll say it's increasing over all real numbers and it's never decreasing. As a reminder, at any point, you can pause this video if I'm going too fast or even slow it down. The last parent function we're going to graph is the cube root function. Now, the cube root is the inverse of a cube. A lot of red. And just like with the square root, we want to pick good numbers. We want to pick inputs and pick x values that make the argument a perfect cube. So again, what's the argument? The argument is everything under stuff under cube root. Okay. So we want to pick anything that makes this value a perfect cube. So I'm going to pick 0, because that's easy, -1 and +1. So I'm kind of working backwards. What's 2 times 2 times 2? 8. So the cube root of 8 will be 2. Now, if I have -2, -2 times -2 is 4, times another -2 is -8. What number multiplied times itself is -1? What number multiplied by itself 3 times is 0? So we have a cube root function that looks like this. The domain of this function, I think this could come up. Now, when I look at the domain of this function, this one's pretty easy to see because as I look at the graph from left to right, I notice it's like it covers everything. So the domain is all real numbers. The range, even though I don't see it, this graph continues to go up. It's just going up kind of slowly and down slowly. If I were to grab my highlighter and trace it from left to right, it's always increasing and never decreasing. Now that we've looked at the four parent functions, let's start to use our knowledge of the parent functions and our knowledge of transformations to graph some transformations. So before you even start anything, I want you to pause the video and think, what transformations are being applied to the parent function and what is the parent function? Okay, hopefully you came up that the transformations are we are moving right 3, we are moving up 2. And you thought to yourself, aha, the parent function here is x squared. And normally x squared has a vertex at 0, 0. But if I'm going right 3 and up 2, now I've got a vertex. Oops, that's not. I have a vertex right here. So right 3 and up 2. I'm going to put that in the middle. This is my vertex. Now, what I'm going to do is I'm going to go 2 points higher for 5 and 2 points lower. And I'm going to either know what I know about the shape of this graph, or, and I will demonstrate this, I'm going to substitute these purple values. I'm going to color code a little bit. So here I've got 1. So I've got 1 minus 3 squared plus 2. 1 minus 3 is negative 2. Negative 2 squared is 4. 4 plus 2 is 6. So now for 2, 1 minus 2 is negative 1. Squared is 1. Plus 2 is 3. Now, here's the beautiful thing about a parabola. Parabolas are symmetrical around the vertex. If I find these two values, I know these two values. Now, you could have done the positive ones also, like 4 minus 3 is 1. 1 squared is 1. Plus 2 is 3. 5 minus 3 is 2. 2 squared is 4. 4 plus 2 is 6. So you can use that symmetry to save you a little time. Let's get these plotted. I've got the vertex is 3, 2. Now the domain, I can substitute any x value into this equation and I can evaluate it. This graph stretches from left to right. For either of those two reasons, I can say the domain is all real numbers. But the range is not all real numbers. Look at the graph. What's the lowest y value you see here? Y value. And hopefully you notice the lowest y value is 2. And everything higher than 2 is on this graph. I don't know why we're missing increasing and decreasing. Let's just write those in. Get our highlighter. Now left to right, as I start tracing on the left, the graph is decreasing. It decreases until 3. So I'm going to make a note, decreasing when x is less than 3. And then after 3, it increases. It's increasing after 3 when our x values, because like after 3, 4, 5, 6, these are all increasing values. So what we're going to do for the rest of this lesson is you are free to continue with the video, or you can pause and then just kind of use the video to check your work. We're going to continue using our knowledge of parent functions to graph 3 more graphs using transformations and a parent function. Number 6, we now have a square root. This one might be a little tricky. The first thing I should identify is the endpoint. And again, the endpoint comes from the fact that this goes right 3 and up 2. So I have an endpoint of 3, 2. 3. I don't have any dilation here. So I'm going to start at 3, 2. And I know I have to pick numbers to put here that make it nice. Like, for example, if I put a 3 here, 3 minus 3 is 0. The square root of 0 is 0. That's happy. Like 3 minus 3 is 0. Square root of 0 is 0 plus 2 is 2. What I don't want to do is just start to throw numbers in here. I want to think, what will make that argument a perfect square? So I'm going to think x minus 3 has to equal 0, 1, 4, and 9. I'm going to solve this mentally. Like x minus 3 equals 0. If I add 3 to both sides, well, I already have that one. If I have x minus 3 equals 1, and I add 3 to both sides, I'm going to get 4. Now watch what happens when I substitute 4 in. The square root of 4 minus 3 is 1. 4 minus 3 is 1. The square root of 1, I can do that. That's just 1. So now if I do x minus 3 equals 4, if I add 3 to both sides, I get 7. Again, watch what happens. When I substitute 7 in, 7 minus 3 is 4. The square root of 4 is 2. 2 plus 2. Right, and let's do one more. If I do x minus 3 equals 9 and I add 3 to both sides, I get 12. If I go the square root of 12 minus 3, that's 9. Square root of 9 is 3. 3 plus 2 is 5. And so by taking a minute to think about x minus 3 equaling my perfect square numbers, what x values should I pick? I end up with inputs that come out beautifully. I don't have any weird decimals to worry about. 5, 6, 7. 12 is, I can't do that guy, sorry, friend. Now, the domain and the range for this are not all real numbers. Pause the video and write down what you think the domain and the range will be, and then unpause. Hopefully, you wrote the domain is x is greater than or equal to positive 3, because the graph starts at 3, and then every x value after that has a value on the graph. For the range, hopefully you wrote y is greater than or equal to 2, because we have a value at 2, and then we have a value everything above that. Let's take a look at number 7. So I want you to pause the video and think, what are the transformations? What is the parent graph? Hopefully you thought the transformations are left 1, down 5, and it's a cubic. So if a cubic does not have a vertex, it does, however, have a point of symmetry. Right. So cubic functions are not weird functions. I can cube everything. I already know the domain and the range will be all real numbers because of the shape. So I have -1, 5, and then I can go 0, and I'll just substitute 0 in here. 0 plus 1 is 1. 1 cubed is 1. 1 minus 5 is -4. Now I'll put the 1 in here. Let's switch colors. I've got 1 plus 1 is 2. 2 cubed is 8. Minus 5 is -3. And then if I do the arithmetic for the other two, I will get -13 and -6. So let's go ahead and get these graphed. Oh, wait a minute, I got a mistake here. This should be a 3. Because I should have 8 minus, I don't know why I said that. We have 2, 3. We have 0, -4. We have -1, -5. -2, -6. I don't know that I can get -13. That's really low. But what I'm just going to do is I'm going to bring it kind of steep because I can't reach -3. Every single x value can be evaluated. At some point, this graph is going to touch every single y value. All right, the last one we look at will probably be the trickiest to graph. Let's start the same way we've been starting the others. Let's identify the transformations and also identify the type of function we're working with. What are the transformations? Hopefully you notice the transformations were left 1, down 5. That gives us our point of symmetry. So I'm going to put that in the middle of my table. So now, because this is a cube root, I need to be really smart about this. I need to pick numbers that make the argument, that make the x plus 1 a perfect cube. So I already have the x plus 1 equals 0. This is the x plus 1 equals 0 because if I have x plus 1 equals 0 and subtract 1 from both sides, negative 1. So now I'm going to think about x plus 1 equals 1, x plus 1 equals 8, x plus 1 equals negative 1. So go ahead, jot these down and write down what, if I were to solve these 4 little equations, what would I get? Hopefully you wrote down 0, 7, negative 2, and negative 9. These are going to be the other x values we use in our table. Watch what will happen. We did a little bit of work. This is just a little bit of work. These are 3 little baby equations. Watch what happens arithmetic-wise. Let's start with the 7. If I substitute 7, the cube root of 7 plus 1 minus 5. 7 plus 1 is 8. What number multiplied 3 times gives us 8? 2. Cube root of 8 is 2, and then minus 5 is negative 3. As we substitute these, and I'll do one more all the way out, let's do 0 next. The cube root of 0 plus 1 minus 5. 0 plus 1 is 1. The cube, what number multiplied 3 times gives us 1? And then minus 5 is negative 4. If we go through and do this, 6, that'll be negative 8. The root of negative 8 is negative 2, negative 7. We've got all our points, and they're all nice integer values. So here, oh, I missed. Here is our cube root that has been moved left 1 and down 5. I missed a little bit, that's okay. It has a domain of all real numbers because it stretches from left to right. It has a range of all real numbers because it stretches from bottom to top. Your homework tonight is actually not to produce any graphs. We will work more on graphs on Monday. Your homework is to work on pages 13 and 14. I think there are other two graphs. I think there might be some on 14. Yes, there are some on 14. They're not so bad. There are answers posted. I will scroll through them on this video so you can look at them if you're needing to check. They will also be posted on Google Drive.